Okay, welcome back everybody. This morning I presented a lecture in class, so we did meet in class. I had a technical issue, so I'm re-recording everything, or I'm actually recording it for the first time right now. So I'm going to recap what we said in class. We went over introduction into point estimators. And there's lots of interesting things that can be said about point estimators. I alluded this morning to how you infer the variance in a normal model, and it depends. It depends on if you actually know what the mean of the model is. Depends on if you need to estimate x bar, or we need to estimate mu with x bar. Do you divide by n or n minus 1? And we had a little discussion about all of it. I'm not going to continue that discussion here. We'll pick up on Monday with examples of which estimators do we use that pertain to the midterm that you just turned in. We had a little dialogue about that, and I'm going to forego that because some of you are still turning in your midterm right now. So please get that to me as soon as you can, and I'll get those graded for you as soon as I can. We'll jump into point estimation in just a moment, and I'll recap what we talked about this morning. Mainly, we're going to discuss the negative binomial distribution. So we're going to be using that through our examples. Mohammed's going to come in on next Monday, so not this Monday, but next Monday. That'll be the 29th of March, and he'll give you a discussion on the likelihood principle. We'll allude to the likelihood principle throughout this class, but we're not going to make it a mainstay of this course. So I've said many times, it depends on the day of the week how I feel about the likelihood principle. I do like operating off of likelihood functions, so I take that near and dear to my heart. The likelihood principle is a little bit too strong of a statement that says that if you have two likelihood functions that are the same, then you should come up with the same inferences. And for me, that's true. For other people, that might not be true. Mohammed will give you a full breakdown discussion of that, and we'll allude to it throughout this class. I've also said we're not really going to talk about completeness in this course, but I'll say a few comments about it. Mohammed gave us a nice discussion on Slack. So you can look over his notes that he sent to you, but he gives you some intuitive rationale for understanding when a statistic is complete. Now I'll say the only relevance of this is that usually we think of sufficient statistics as having all the information that you can get out of a sample for inferring theta, the parameters of the model. And ancillary statistics are kind of the opposite in some sense, that they have no information about the parameters. And that's true marginally, but there might be some overlap there. And we discussed this in our example from the last lecture that I gave you, the last recorded lecture. So completeness is a type of statistic. Complete statistics are such that when a sufficient statistic is complete, it has no overlap with an ancillary statistic. That's mathematically interesting, almost of no practical value though. And so we've used the term orthogonality when we talk about all this. I just want to point out, this is the orthogonal condition right here. And so Mohammed gave us a nice way of thinking about this. That he said that this really is, if we think about it in a discrete case, this is just going to be, expectation is going to be this sum of the GTs. So if I'm thinking about these discretely, then this is going to be the probability function of the T's given theta. And this will go from whatever the support of T is. So we'll sum over I. And another way to write this down is just to enumerate out my GTs. This is going to be just a vector, so commas, GT, and I'll say this has some support. I'll say it goes out to K right here, and this is going to be multiplied by this vector. So this is going to be the probability distribution Give myself a little bit more room. Well, the ti is given theta, dot, dot, dot. This is going to be t1 out to the probability of tk. That's the support. Those are all the different values t can take on. So t can take on some number of values. This is that expectation. So I goes from 1 to k. And I'll just label that. And this is the number of elements t can take on. So arbitrarily, t can be any statistic, and we can follow this framework for completeness. Where we usually invoke it is in minimal sufficiency. So if a minimal sufficient statistic is complete, it adheres to this right here, that the expectation that some function, and this is an arbitrary function, if the expectation of that thing is 0, i.e. when I dot product, so that's the dot product right there. If it were continuous, we'd just replace this summation with an integral and the same definition would apply. It's saying that for an arbitrary function, if the expectation of that statistic is 0, then that statistic itself, gt, is 0, is what this says. So the probability of gt being 0 is equal to 1. There's a small nuance in here that says on an unmeasurable set, it could be something different. So the set has to have measure 0. In our discrete formulation, this would say that gt is identically 0. So everything in discrete land can be measured. An element is an element, has the same measure of every other element. So this condition would be that gt is identically 0. In a continuous fashion, this could be 0 on an unmeasurable set. We don't need to think about that too much. But the comments on completeness are just this intuition as to why is this the condition that the expectation of gt is 0, and we can think about it through the dot product right here. And so this is equal to 0. In a lot of times we'll say this means it's orthogonal. So we're taking some verbiage out of physics land, and we're thinking about when the dot product is 0, things live at a 90-degree angle. If you remember that from physics. In our mathematical sense, we apply this, we think about it in terms of orthogonality. I guess I think about this geometrically as living in a right angle, but I'm not actually thinking about triangles or something like that. I'm just thinking about this mathematical condition that says the dot product is equal to 0. What this means when the dot product is equal to 0 is that things live in non-overlapping spaces. So I'll just write this down, non-overlapping. And it just means that this is true. The dot product is equal to 0. So that thing is equal to 0. What that means is that the information in this vector and the information in this vector don't overlap each other. So there's no overlapping information. This doesn't depend on theta. This does depend on theta. And so what it's saying is that the information supplied in theta and the information supplied without theta are wildly different. They're different information. There's no overlap. So Bassu's theorem is a statement about minimal sufficient statistics that adhere to this criterion don't overlap any ancillary statistics. What do you do with that in practice? Nothing. So some could argue that the conditional frequentist, the conditions on ancillary statistics, would want to be aware of this. We're not going to touch this here because there's no formal paradigm for applying that conditional frequentism. What I like about Mohammed's comments are the insight on why this condition right here, that the expectation of any arbitrary function without the parameter is totally different from information that contains the parameter. I'll let you think about that a little bit more, but we're not going to dwell on it in this class. If I do test you on completeness, it's just going to have you to write down this definition. Maybe to write down Basu's theorem. We're not going to prove it in this class, but there is an intuitive construct as to why this is the definition of no overlapping information in functions that don't contain the parameter and functions that do contain the parameter. For those of you that are a little bit more abstract, this will make sense. For those of you that are practitioners, don't worry about it any further. Okay, so I'm going to move on from there. We're done with this. And I want to talk about point estimation. I want to start with an example. And I want to think about a mechanism for constructing data. So this is just going to be a Bernoulli. So Bernoulli with parameter p. So what I'm really thinking about is that I have elements that are either going to be heads or tails. So I'm flipping a coin, and that's going to happen with probability p or 1 minus p. Everything in my example is IID. So I'm just flipping the same coin every single time, and I'm flipping it the same way. Let's imagine that I had this mechanism right here, that I knew I was flipping a coin, and I observed some data. So the observation, and I'll just make this up real quickly. Might look like this. So maybe I got a heads here, tails, heads, tails, tails. I'm going to say a head is here, and I'll put in some heads here. Let's imagine that you didn't watch me draw that. So you have no idea what I was thinking about as I enumerated all of this. But what I want to point out is that there's 1, 2, 3, 4, 5 heads, and there's 5 tails. 1, 2, 3, 4, 5. And so there's the number of draws. I'm going to denote that by K. A lot of times I write this down as N, but I want to discuss the number of draws a little bit differently this time, so I'm going to give it some new notation. Number of draws is 10. There's 10 times this coin was flipped. And the number of successes, which we're denoting as a heads, so I'll call those successes, is equal to 5. Now imagine I came into this problem and I agreed that this is how the data was generated. It's just an IID coin flip, and I saw this right here. There's an important question to ask yourself as to why did we see 10 observations? There's 2 different ways you can think about this. There's probably an infinite number of ways you could think about it, but I'm going to give you 2. So imagine I have 2 different experimenters. So experimenter 1 believes the data was flipped, or the data was constructed such that K equals to 10 was fixed. So the number of coin flips was predetermined. And X, the number of successes, I'm going to say this is X right here, is equal to 5, was random. So just to recap, I predetermined experimenter 1 thinks that the data was constructed such that it was predetermined that they would flip the coin 10 times. And the number of random things were the number of heads and tails. Okay, so if the heads are random, the tails are also random. The number of times the coin was flipped was predetermined and it was fixed. Experimenter 2 thinks that the data was generated such that we would flip the coin until we saw the 5th heads. So number of successes was predetermined. Is fixed. So this is x is equal to 5. And the number of trials is random. We had a discussion about these distributions this morning. This is binomial. Experimenter 1 is binomial. And experimenter 2 is assuming that the data came from a negative binomial. Okay, this is not well named in the rules that we follow in naming distributions is wildly inconsistent. Log normals, inverse normals, for example, they are not telling you how things are constructed. So a log normal is the distribution such that if you take the log of it, it's normally distributed. Inverse normals are not that. It has to do with a waiting time until you strike something. And so it's an inverse process, but not in ratio. The negative binomial further convolutes the language. So this doesn't mean the opposite of positivity. This means something different. It means the inverse relationship that we observe in the binomial distribution. So k is fixed, x is random, k is random, x is fixed. So we're switching those roles, and somebody thought that would be a good idea to call that the negative function. I probably would have called it the inverse relationship, saying that that's not a good naming construction either. So negative binomial is the probability distribution of the number of draws that we have until we see some predetermined number of successes. We could also think of this as being, in terms of a negative binomial distribution, we could be thinking about this is the number of failures is random. So I'll just write that down. So I'll just say this is what we observed. Regardless of how we think about this distribution, I'll just say down here, or number of failures is random. I'll help you to derive these distributions in just a moment. I just want to write down some things I know about these distributions, and I'm going to leave it to you as a mental exercise to be able to convert back and forth between which version of the negative binomial we're using. Are we talking about the number of failures being random or the number of trials? So I'll just write down an equation. The number of trials is equal to the number of successes plus the number of failures. So this is successes, and this is failures. And that makes sense. The number of successes plus the number of failures is equal to the number of trials. And we can rearrange this any number of ways. So I could write down that y is equal to k minus x. So let me just write down what this distribution looks like. So the negative well, let's start with the binomial. So binomial distribution is going to be k, choose x, p to the x, 1 minus p to the k minus x. And a lot of times we write it down this way. I could further confuse you and call that y. So k minus x is equal to y. What's random right here? X is random. So it's usually polite to notate very explicitly what is random. So write it into your equation very clearly. So random is that. This whole thing is random right here because x is random. And that's random. And the fixed part of this equation is k. So this is fixed. So if we think about the negative binomial, it looks like this. And I'll drive this in just a moment. This is going to be k minus 1, x minus 1, p to the x, 1 minus p to the k minus x. Okay, so what's random in this equation? It's this stuff. So I'll just say this part is random. Whereas this part is fixed. So a different way of viewing this same data set. Just to touch on something Mohammed's going to say is these two functions right here have the same likelihoods. What the punchline to his lecture is going to be is if you use p-values and you sum over tail probabilities, this normalizing constant comes into effect. And you'll compute two different p-values depending on how you view this experiment. The likelihoods, however, are the same exact thing. And I would say I'm a likelihoodist, that I like likelihood functions, and the fact that these have the same likelihood functions would tell me that I should come up with the same inferences. Mohammed will go into greater detail about that. There's no necessity to follow that rule. I happen to, but that's not really a big deal. Basically, these distributions look the same up to their normalizing constants. And I'll help you to think about this normalizing constant in a moment. I will say that we could write down the expected value for this problem. So for the binomial, the expected value of x is equal to k times p. And for the negative binomial problem, I'm going to parameterize it just a little bit different. I think I may have done this wrong this morning when I wrote it down. But this is going to be expectation of the number of failures. I'm going to write it down like this. Expectation of y, so this is my failures, is going to be equal to x times 1 minus p over p. Now it makes a little bit of a difference when you write all this down. So I might, instead of writing everything down in terms of k right here, I could rewrite everything in terms of y. by using this equation right here. So everywhere I see k, I'm going to replace it with a version of y. I'm going to replace it with that one right there. So this is going to look like x plus y minus 1. Choose x minus 1. Or you could choose y minus 1. It doesn't make any difference. So this is going to look like p to the x, 1 minus p to the y. So I'm just rewriting that a little bit differently. And so if I wrote it down like this and I thought about everything in terms of k, so if I wrote down this is a function of k given p, I might write it down like this, and then I would have to tell you where k goes from. So k, the number of trials that I can have, is going to have to start at the number of successes. And that goes on infinitely. If I think about this in terms of y, then I could write down, this is going to be my number of failures right here. This is going to go from 0, 1, all the way out to infinity. And so these are just shifts. So again, this is the number of trials. If I have x fixed successes, how many times do I need to flip the coin until I see my x success? In this example, it's 5. Well, I need to flip the coin at least x times. In our example, we need to flip the coin at least 5 times. And so that would be the minimal number of draws I could get before I get to the x success, the 5th success in our case. Or I can talk about the number of failures, and this would be identical. If I flip the coin only x times, it means that I saw 0 failures. So this is just shifting the process. This is just a shift. When I wrote this down this morning, I didn't say what the random variable was right here. So that's a little bit confusing, and I can see where that confusion arose. If I wanted to come up with the expected number of draws, for instance, so if I wanted to look at expected number of trials, how many times do I flip the coin until I see the x success? All I have to do is reshift the process. So this is going to be equal to x 1 minus p over p plus x. This is going to be the number of trials that I have right here. So if I want to talk about the expected number of trials, I can just shift the expected number of successes. And there's a different way you can write this down. So this is just equal to x 1 minus p over p plus 1. So I factorized out the x. I'm going to rewrite that just a little bit. This is going to be 1 minus 1 over p. Or this is going to be, let me redo that. 1 over p minus 1. So those cancel each other, and this is equal to x over p. So 2 different expressions depending on which thing I'm thinking is random. So this is the expected number of failures, is that. The expected number of trials is that. Ankur, you said it correctly. We were just debating over what is the random variable. This seems to confuse a lot of people. Both are correct. Just keep in mind, we're talking about 2 different things being random. I usually think about this in terms of the number of failures, but it doesn't matter how you think about it. Let me derive this distribution for you and show you that this is the correct normalizing constant. Next time when we pick up, we're going to apply MLEs to this distribution. We're going to apply the method of moments estimators, and we're going to do a Bayesian analysis on this. But I just want to walk you through what is a negative binomial. So let's just erase this. Okay. So if I'm confused and I want to think about what does a negative binomial mass function look like, all I have to think about is really this picture that I've drawn, which is really simple. I want to point out that this happened with probability p. So this last observation happened with probability p when we flipped that coin, and it ended the process in terms of the negative binomial distribution. So what's random here, all this stuff is random. So in a negative binomial experiment, I always get to see the final trial being a success because that's what ends the trial. And we're waiting to see our fifth success. So what's over here? This is going to have k minus 1 elements. There's 9 in this case. And out of all of this, we know that we're going to have 4 successes. That's 5 minus 1 is equal to 4. So all our successes are heads. There's 4 of them here because that one is the 5th one. So this is going to be x minus 1 successes right here. What's the probability that this thing happened? It happened with probability p. What's the probability that all this stuff happens? It happens with k minus 1, choose x minus 1. P to the x minus 1, 1 minus p to the y, if I wanted to write it down that way, or I could write it down as k minus x. Same exact thing. So we have to be careful with this distribution, but we can always derive things from first principles. So from now on, when you see a negative binomial distribution, notice that this is anchored with probability p, and this stuff happens binomially. So all the precursors to the last element. So this right here is binomial. This thing right here happens with probability p. So that's this element. And so this right here is k minus 1. Choose x minus 1. P to the x. P times p to the x minus 1 is p to the x. 1 minus p to the k minus x. Or if you prefer to parameterize everything in terms of y, you can do that. So this is y right here, and k is equal to x plus y. Right there. So I can think about it 2 different ways. If I discuss y being random, y has support 0 through infinity. K has support, if I'm thinking about k as random, x all the way up to infinity. This seems to be something that can confuse most students, so hopefully this helps clarify some of that. So back to the problem at hand. What do we believe p is? So let me just actually walk through the first analysis. We noticed that if we maximize this function, regardless if we thought everything was binomial or negative binomial, the likelihood function is the same. And everything will maximize to be the exact same thing. So let's just walk through that real quick. And this is where we'll pick up next time. So the maximum likelihood. Estimator. I like the name of this estimator because it tells you exactly what you do. What is the likelihood? Experimenter 1 thinks that the likelihood looks like this. Given all of my data, I'll write it down in terms of x, is equal to k, choose x, p to the x, 1 minus p to the k minus x. Right here. This is going to be proportional to p to the x, 1 minus p to the k minus x. Experimenter 2 thinks something slightly different. So experimenter 2 thinks the likelihood function given, I'll write it down in terms of y, is going to be x plus y minus 1, choose y minus 1. So I wrote it down a little bit differently. Instead of writing down x minus 1, I wrote down y minus 1. They're exactly the same, and I'll let you convince yourself of that. So same numbers, this whole thing. Y minus 1 and x minus 1 might not be the same, but this combinatorial factor is the same. Times p to the x, 1 minus p to the y. That's k minus x. I could write it down that way. And this likelihood function is the same as that one. So experimenter 1 and experimenter 2 have the same likelihood functions. If they were going to try to maximize that likelihood function, it's not the only gig in town, but you could do that. You could say the most likely value is the one that maximizes this function, and they'll maximize it exactly the same places. So let me write that down, what this looks like. In either case, both experimenters will come up with the same conclusions. So max likelihood. What I want to do is I want to take a derivative with respect to p to the x, 1 minus p to the k minus x. I'll write it down that way. And I want to set this thing equal to 0. So I want to just point out that as soon as I do this, I need to put hats on everything because I'm solving for something. So this is a procedure. So I want to take this thing after I do it, and I want to plug in p is equal to p hat right here. I wouldn't solve it this way because I'd have to do a lot of product rule and things of that nature. Most of us get used to linearizing our equations through taking a logarithm. So this is equivalent to taking the log of p times 1 minus p x k minus x is equal to 0. And of course I want to solve this to be p is equal to p hat. So as soon as I say this is equal to 0, I've invoked a process and I'm coming up with a specific estimator for p. And we always denote that different from the true parameter, and we usually put a hat on top of it. This is an easier problem than that one. It just takes less lines of mathematics. So let me just do that. So I'll just take the logarithm. This is going to look like x log p plus k minus x log 1 minus p. And I'm going to take the derivative of this thing. And that's pretty easy to do. Hopefully I can get my negative signs right and apply the chain rule properly. Let's see how I do. So this right here is going to be x derivative of logarithm of p. Which logarithm did I use? I used the natural log. It makes it easier. If you use any other log, it'll be fine. Everything will be off by a scale factor, and when we set everything equal to 0, it won't make a difference. I'll just point out that if I had some normalizing constant right in here, it would cancel out as soon as I set everything equal to 0. And so I never put it in to begin with. I'll let you think about that. So this is going to be plus k minus x. Derivative of this function right here is 1 over 1 minus p. And then I need the chain rule. And the chain rule of the derivative for 1 minus p is just going to be a -1. And so I'll just switch that to a negative sign right there. That's the chain rule. Now I'm going to set everything equal to 0. So let me just do this on a different line. We'll do this again next time. This is going to be x over p minus k minus x over 1 minus p. And so as soon as I do this equal to 0, this is the MLE procedure. I'm maximizing the function. I should check the endpoints and whatnot when I do that, but I also know that this thing is monotone. So I'm not going to do it just for the essence of time. As soon as I set that equal to 0, I have to put the hat on everything. So I'm invoking a particular estimator. Which estimator am I coming up with? This is the MLE. And so I might denote that and write down MLE right here. But that's a bit redundant because I know how I came across it. So I'm just going to get rid of that. And now I just need to solve for p hat. So once I solve for p hat, I won't go through the details because you can all do this, that p hat is going to be equal to x over k. And this is going to be equal to the number of trials divided by the number, this is the number of successes divided by the number of trials. In experimenter 1 or 2, if they were using maximum likelihood estimators, would come up with exactly the same inferences. What I'll walk you through next time is how to do method of moment estimation. But just as a prelude to that, what we're going to do for MOM estimators so sometimes we call these MOMs. And that usually incites a lot of snickering. Poor moms. They never get a break. What we'll learn next time is, though, while all our moms are great, method of moment estimators might not be so great. This example will not show us that. So what we're going to do is we're going to take the experimental moment and we're going to set it equal to, and as soon as we do this, we've invoked our MOM criterion. We're going to end up setting it equal to our theoretical moment. And we'd have to do this 2 different ways depending on if we thought that the procedure was binomially distributed, our data was binomially distributed, or if our data was negative binomially distributed. We'll come back next time and we'll work on this. So our experimental moment is going to maybe look something like this, xi's divided by n, and our theoretical moment is going to be expectation of x right here. Or we could end up doing in experimenter 2, so this is experimenter 1. Experimenter 2 will do something slightly different. And they would write down their average failures, yi's, divided by n, I goes from 1 to n, is going to be equal to the expectation of y. So we would end up solving for this right here. This right here is k times p, and this right here is going to be x times 1 minus p divided by p. I'll let you work through those details, but what you're going to find out when you do this, both answers are going to yield the same thing, that we have the number of successes over the number of trials, which is sensible. The punchline here is that we can have different procedures for coming up with estimators, but we still need to evaluate how good that estimator is at the end of the day. I'll point out, it's good to match moments that contain your sufficient statistics. So our sufficient statistic in both of these problems, regardless, if we think about everything being binomially distributed or negative binomially distributed, these are our sufficient statistics. So if you tell me the sum of the xi's, I'll tell you the sum of the yi's. If you tell me what k is. Oh, and I messed this up. I'm so used to writing down n that I do it automatically, but in our problem, this would be k. So we'll pick up next time with this. I just wanted to fill in the gaps from this morning. The main point here is that you understand what a negative binomial is, and you know what its parameterization is, and you can shift back and forth between the two different parameterizations that your book uses. It's not that confusing, but it's definitely hard to memorize. So don't memorize it. Think about reconstructing that distribution from scratch. That's it for now, and I'll see you all on Monday. Have a great weekend.